Welcome to the Explainer. Today, we're going to completely flip how you look at the ocean. Seriously, we're looking up, straight into the sky. We all kind of think we know exactly what drives the rhythms of the sea, right? Well, we're going to strip all those standard assumptions away. Instead, we're exploring this massive, invisible, planetary scale mechanism that pushes the water around in ways you probably never even imagined. Check out this quote from Thomas Hardy: "Distilled by the sun, renewed in a year, in a day, or in an hour." It's poetry, sure, but it perfectly sets the stage for a mind-blowing scientific reality. The sun is directly manipulating the sea. It's not just a romantic idea. Hardy actually nailed a deeply physical thermodynamic process that's literally reshaping our global oceans hour by hour. So what if the ocean was controlled by an invisible thermal engine? Let's dive right in, because this is a total paradigm shift. For this explainer, I need you to completely forget about the moon. Seriously, ignore lunar gravity altogether. No moon. We're talking pure solar thermodynamics today. We're looking at a thermal engine that drives the ocean's behavior using absolutely nothing but the immense heat of the sun. Here is our roadmap for tracking this planetary machine. We'll start with the global thermal engine, move to the S1 solar tide, hit the ocean's double effect, check out the inverse barometer stump, and then wrap things up with a crazy fast climax, transient pressure theory. All right, part one, the global thermal engine. Let's see how this massive system builds across the entire planet. Now just look at how these two hemispheres contrast. On the sun-baked day side of Earth, we've got direct solar heating. That constant radiation causes the atmosphere to expand and rise. But then look at the dark night side. The exact opposite is happening: rapid cooling, sinking air, and super dense atmospheric displacement. It's this wild global duality of temperature and pressure. And this perpetual cycle, it's not just random weather. Thanks to the constant absorption of solar insolation, specifically the heating of ozone and water vapor way up in the upper atmosphere, we get this relentless kinetic chase. The cold, dense night air is continuously chasing and displacing that expanding, warm day air as the planet spins. It essentially acts as this giant breathing thermodynamic machine driving our entire atmosphere. Which brings us to part two, the S1 solar tide. This is where that huge atmospheric energy actually starts messing with the sea. Now, the absolute most crucial thing to grasp here is that the S1 tide is not gravity. Look, when we hear the word tide, we instantly think gravitational pull, right? Throw that out. The S1 is a purely radiational atmospheric tide. It's a daily wave in the atmosphere, driven entirely by the sun's continuous heat, locked strictly to the 24-hour solar cycle. Because the Earth rotates eastward beneath the sun, all this thermal heating creates a massive atmospheric wave that propagates to the west, perfectly synced up with the sun. Just picture it. As the planet turns, this huge pressure wave sweeps continuously across the globe, carrying the sheer weight of the atmosphere, getting ready to literally slam into the water below. And that leads to part three, the ocean's double effect. Let's track that atmospheric energy all the way down to the surface and see the impact. This is so brilliant because the sun is actually attacking the ocean from two entirely different directions at the exact same time. Step one is direct thermal expansion. The seawater absorbs the sun's radiation and physically swells up from internal heating. It expands outward. But then, boom, step two is the kinetic counterpunch, the inverse barometer effect. That moving atmospheric wave we just talked about, it physically stamps down on the ocean from above. So the water is being forced to expand from within while getting crushed by a heavy atmospheric footprint from the top. Moving into part four, the inverse barometer stamp. Let's really zoom in on that intense downward pressure, because the physical mechanics here are crazy precise. You can kind of think of this effect like a giant planetary thumb. The inverse barometer effect is just the localized sea level trying to balance out changes in atmospheric pressure. So wherever that atmospheric S1 wave cranks up the pressure, the sheer weight of the sky literally stamps a depression right into the ocean. The sea surface is literally forced to hollow out to balance that atmospheric load. Let's look at the highly specific math behind this footprint, because the sky doesn't just push the water randomly. It follows a very strict ratio. For every single hectopascal, you probably know it as a millibar, increase in atmospheric pressure, the ocean is pressed down by exactly 10 millimeters. No more, no less. This means the sky is locked in this vast, fast-moving balancing act with the sea, basically equalizing the weight and literally carving the ocean's surface millimeter by millimeter as that thermal wave passes overhead.
And we aren't just theorizing here. You can actually see the S1 solar wave leaving its distinct mark on these VLBI measurements that track Earth's rotation and surface displacement. But looking at this real-world data raises a huge question about the physics of water. Think about it. If a 10-millimeter depression has to perfectly track a globally moving atmospheric wave, how on Earth does this incredibly dense, heavy ocean react fast enough to get out of the sky's way?
Well, that brings us to part 5, transient pressure theory. To understand how the ocean moves so insanely fast, we have to completely rethink water as a medium. Usually, we picture water slowly sloshing out of the way when you apply force. But under a sudden, massive atmospheric load like this, the ocean does not gently yield. Instead, it acts as a super stiff, highly pressurized conduit. It takes that atmospheric stamp and transmits it internally, not as a slow, lazy swell on the surface, but as a literal fluid shockwave blasting through the water column. And here is the absolute most staggering part of this whole thermal engine. It all comes down to pure velocity. When that atmospheric stamp hits the surface, it triggers what fluid dynamicists call a Joukowsky pressure rise. It's this sudden, intense spike in internal fluid pressure. And because the ocean is acting like that stiff conduit, the pressure wave travels at the speed of sound through the fluid. Sonic velocity in water is a blistering 1,500 meters per second. Because it's moving at sonic speed, the ocean's hydrodynamic response to this invisible solar engine is practically instantaneous. The sky stamps down, and the ocean balances the load at the speed of sound.
It completely rewires your perspective, doesn't it? The ocean isn't just a bathtub slowly sloshing back and forth under the pull of the moon. No, it is a sonically reactive fluid conduit, constantly being shaped, stamped, and molded by an invisible thermal engine driven purely by the sun. So next time you look out at the sea, I want you to ask yourself, are you just looking at water, or are you actually witnessing the high-speed footprint of the sky? Thanks so much for hanging out for this explainer, and I hope it leaves you eager to uncover even more of the invisible forces shaping our world.